Welcome to the educational course Beyond Blobology Advances in Statistical Inference for Neuroimaging. Today I want to talk about classical inference and its caveats. Part 1. Inference in functional MRI. When reading literature about functional MRI studies, you often see these images of brains with blobs or clusters of activity on them. And today I want to talk about how these images come about. For most functional MRI studies, the measured signal comes from distinct locations in the brain called voxels. And these voxels, they span a three-dimensional grid of about 3 by 3 by 3 millimeter cubes across the entire brain. Inference in functional MRI is done on each of these locations or voxels separately. So the maps that you often see are the outcomes of this inference, usually in the form of Z or T statistic indicating significance. The outcomes that you see are usually the statistics values for a certain contrast, for example rest versus task for within subject's design, or group A versus group B, where you have the comparison between activity in the brain for group A versus group B, for example. And these statistics values, they can be converted into p-values and subsequently also in z-values. And the p-values is what we're going to talk about today mainly. And note that these p-values can also be obtained using permutations or randomization designs. So the ultimate goal in fMRI inference is of course how to decide which areas of the brain are active, or more active in one condition than another, or more active in group A than in group B. Most of the time for this we use classical null-hypothesis testing. So for each voxel we state two hypotheses, H0, which is the voxel is not active, and H1, or the alternative hypothesis, that states that the voxel is active. And on the basis of these two hypotheses we want to decide per voxel whether H0 holds or H1 holds. So how do we do that most often? We do that by calculating a p-value that conveys the surprise of observing the data when actually the null hypothesis is true. So in classical inference, there are four possible scenarios to decide if a voxel is active, yes or no. So on the rows that you see here, we have the reality, so whether actually the null hypothesis is true, so that there's no effect of that voxel in real life, there's no activation, or we see the reality that the null hypothesis is false, so that means that that voxel is actually more active in a certain condition or more active in group A than in group B, so that there is an effect. And of course we don't know the reality, but this is assuming that we should know the reality that there either is no effect or there's a genuine effect. On the columns that you see here, we see the outcomes of our statistical test. So our statistical test, being it a t-test or a z-test or an f-test, can conclude two things. It can conclude that the null hypothesis is true, so the test says there's no significant activation in this voxel, or the statistical test can say that the null hypothesis is false, so we reject the hypothesis, and we say that this voxel is significant. In this case, there are four different options. So we can either be correct, in the acceptance of our null hypothesis, which is a true negative. So in reality, there is no difference between two conditions, and our statistical test says also there is no, this voxel is not significant. We can also have the correct position here, where in reality there is an effect, so this voxel is actually more active in one condition than another. And our statistical test also rejects our null hypothesis and says there's a correct rejection of a null. So the test is significant. So then we have a true positive, where we correctly reject the null hypothesis. In these cases, there are two cases that things can go wrong. So one of the cases is that our statistical test says there's no significant difference between the voxels, between the conditions, and in reality there is an effect. So then things go wrong. In reality there is a difference, so the voxel is active, but our statistical test says that it's not. So basically our test is underpowered. We have no power to detect the real activation. There could also be the case that our statistical test says that there is an effect, while in reality there is no effect. And this is what we call a false positive decision. And this means that we decide that our voxel is active, that there is a difference between the groups, while in reality there is none. And this last one, so the false positive decisions, these are the ones that we want to avoid making as much as possible. When we decide whether we can reject the null hypothesis for a voxel, we allow some uncertainty. And it is basically the uncertainty of making a false positive rejection. So we allow an alpha level chance for falsely rejecting the null hypothesis when the null hypothesis is actually true. So a false positive result. And usually this alpha level is set at 5%. So in 5% of the cases, if I would repeat my experiment multiple times, I would falsely reject the null hypothesis for that voxel. I would say that there is a significant difference, or that this voxel is significantly active, while in reality there is not. So this 5% false positive rate that we allow, so this little uncertainty, is if we do one test, if we would have tested just one voxel. But in functional MRI studies, we don't do just one test, we do over 200,000 often in one experiment. One for every voxel in the brain. And this increases the chances of finding a false positive result dramatically. So out of, for example, 200,000 voxels, 10,000 could be false positives, and that's a lot. So if we don't control, we are in trouble. And this was pointed out by the Salmon of Bennett et al. In 2009. When performing multiple hypothesis tests, we want to control what we call the family-wise error rate. And the family-wise error rate is the chance of at least one false positive result in a family of tests. And we want this chance to be lower than alpha. And alpha we can choose. So instead of saying we want the alpha level for a single test to be smaller than 5%, we want now that the chance across a whole family of tests is no higher than 5%. So the chance of making false positive decisions is now decided on the family of tests, so it's corrected across the entire family that we choose. And the family of tests is usually either all the voxels in the brain or all the clusters in the brain, but there are multiple options. So to summarize this first part, the goal of fMRI inference is to decide for each voxel whether it is active or not, using a hypothesis test. And this active or not is more active in one condition than another, or is more active in a group than another group. It's a binary decision on whether the voxel is significant. And this significance can mean, is it more active in one group than another, or is it more active in one condition than another? But it's a binary test, yes or no, whether it's active, yes or no. And for each test that we do, we allow a little uncertainty of whether our decision is the right one. This is at 5%. But when doing multiple tests, the chances of making a wrong decision somewhere in our family of tests increases dramatically. And that is why the family-wise error rate of our family of tests is what we want controlled. So we want to control the chances of making a false positive decision across all of the tests that we perform. And in this case, in fMRI, it's often across all the voxels that we test. We want the number of false positives to be under control. Now for part 2, multiple testing in functional MRI. Let's start with an example. So here you see data from a study on vocal and non-vocal sounds by Pernet et al. In 2015. And what you see here are the Z values for the non-vocal versus vocal contrast. So this is the activation of an entire group of 66 participants, where the contrast was the activity of the non-vocal sounds is larger than the activity of the vocal sounds. You can see here in red and yellow the positive Z values, and in light blue and blue you can see the negative Z values. And the higher, so the lighter the color is, so the more yellow or the more light blue it is, the higher the Z value is. And you can see a flurry of activity across the entire brain. In total, there were 407 in-masked voxels, meaning that the voxels that are actually within the brain and were scanned for all participants. And for now, we'll just focus on the positive values, so we ignore the negative values for now. The Z statistics that you see, they indicate whether this voxel is more active in the non-vocal condition than in the vocal condition. And the null hypothesis that belongs to that is that the voxel is not active, so that the Z value is actually 0. And the alternative hypothesis is that the Z value is larger than 0, so that the voxel is active. So far, this is the classic framework where we're in. So one way of controlling the false positives across this set of Z values that we have, so across these 166,000 voxels, is to do what we call Voxelwise error control. So it controls the family-wise error rate over all the voxels in the brain, so within the mask, and the family that we then sort of control over are all the voxels that are in the brain. And the easiest method to control the family-wise error rate is what we call the Bonferroni correction. And it's calculated by setting the per voxel alpha level to be alpha divided by the number of voxels. So for example, if we want our family-wise error alpha to be 5%, so that no more than 5 voxels that we test are actually false positive, we test each voxel not at 5%, because that would increase the false positives, but we test it at 5% divided by 166,000.407. So each voxel we test not against this 5%, this 0.05 value, but against 0.000003. What you see on the right side in the image are the voxels that remain. So are the voxels that are significant across this number of tests. So you could see in the left side, you could see the red voxels indicating these are the voxels that remain above this alpha level threshold of 0.0003. And on the right side, you see the original sort of positive Z values, and in blue you see the same number of voxels superimposed on them. So you can see that out of all the activity that exists in the brain, only very small regions with activity remains. So it's not very powerful because there is very little activity, but since our family is all the voxels, we know exactly where the activation is. So we can pinpoint these areas are active, and we know pretty sure that the activity is centered around these locations, around these clusters. So in other words, you could say that we have a somewhat lower power to detect sort of clusters, because out of the entire Z map of Z values that we see, we only see a tiny fraction of it being significant, but we know for sure that the activity is located there. And that's because the chance of any of these voxels being a false positive is smaller than 5%. So the Bonferroni method is the easiest to do, but it's also the most conservative one. It leads to somewhat smaller regions, of course. It's pretty conservative in that sense, especially given that the p-values in fMRI research are often correlated, and that makes it even worse. So additional methods are available, and we're not going to go in depth into them. But for example, you can use random field theory based peak thresholding, which is slightly more powerful than Bonferroni in certain cases. Or you could use permutation based methods with sort of resample the data to decide which voxels are false positives and which are not. Or you can go to false discovery rate based methods. They are often more powerful, but they have weaker control of the family-wise error rate because they do not control the amount of false positives, but only the amount of false positives across the rejected sort of set, so across the significant p-values. You could always say that the false discovery rate methods control the average false positives and not the actual number. Another breed of correction method is what is called cluster extend approaches. So usually we are not interested in like single voxel activity per se. So single voxels are not of interest to us. A more natural unit that we are interested in is a cluster of voxels, which we will name a blob, and hence the name of the course, Advanced Blobology. So we'll look at blobs in the data, and we do inference on these blobs. So a cluster or a blob is defined as a contiguous or connected set of voxels. And we control the number of false positive blobs. So our family in our family-wise error is just all the possible blobs, and this is important to note, it's not all of the voxels. So we control the number of false positive blobs and not per se all the voxels. In practice, we do this using a two-step approach. So first, we choose what we call a cluster forming threshold Z, and we estimate the size of all contiguous clusters above this threshold. So in the image that you see on the right, you can see that we have set a certain threshold, and everything in blue are the clusters that are above this threshold. Then we have to determine the minimum cluster size K that can occur by chance under the null hypothesis in 95%. So given the smoothness of the data and the chosen threshold Z. So this is important that we determine K because this is where we will base our significance test on. And we can do this, for example, using random field theory, or we can do this using permutations. And whatever method you use, it gives you a cluster size K that controls sort of the advent of blobs of a certain size under the null hypothesis. And then the second step is we check which clusters are larger than K, and all clusters that are larger than this value, so all clusters that we find in step 1, we check against this K value. All clusters that are larger than K, we call them significant, and all clusters that are smaller than K, these are non-significant. Here you see an example of different Z thresholds and different K values that are associated with it based on random field theory. So on the left side, the most left side, you can see a Z threshold of 2.3. So everything below 2.3 is discarded, and we count the number of contiguous clusters that are above this Z level threshold. And the associated K value is 597 voxels. So a cluster under this Z threshold and under the smoothness of the data should be at least 597 voxels big in order to be called significant, yes or no. And you can see that the clusters that remain are pretty large and they're pretty widespread. For the if we go one step to the right, you see this Z threshold of 3.1, and then the associated K value is 160. You can see that the clusters become smaller and they become somewhat more localized. But the K is of course also a lower value. So now with a higher threshold, the K value should have only been 160 to be called significant. One step to the right, you see for a Z threshold of 4.0, and there you see that the K value is actually pretty small, it's 25. So the clusters that remain, these are smaller because the threshold is of course higher, but you need the clusters need to be smaller to be significant. And at the most right side, you see a Z value of 5.0, and this is actually the Bonferroni sort of threshold that we decided. And there you can also see that K is 1, so that means that it goes on the single voxel level in this case. So a cluster needs only to be of size 1 to be termed significant, and there you can see that we get exactly sort of the Bonferroni corrected clusters back. So there's a trade-off between the threshold. So a higher threshold has, well, a lower K value associated with it, but of course you find less or smaller areas of activation. So cluster extend approaches are more powerful than Voxelwise approaches, but they are more powerful in detecting activation, not necessarily in localizing it. And this is because of the hypothesis being on the cluster level. Namely that we call a cluster non-significant when the cluster extend is smaller than a value K, and we call them significant when this cluster extend is larger than a certain value K. So no information about the voxels within a cluster is there. So the clusters are either large enough or they are not. An alternative way of stating this is that our null hypothesis is that there is no activation within a cluster because the cluster is not large enough. And the alternative hypothesis, so H1, is that there is at least one voxel active within a cluster. And this brings us to the spatial specificity paradox. So the larger the cluster found, the less we know about activation within a cluster. And this is what we indeed call the spatial specificity paradox. So if we find a very large cluster, like in the image that you see on the right, we can say whether these clusters are significant, and in this case most often the clusters are significant, but we don't know exactly where the activation is. If we go to a higher threshold or go to a Voxelwise approach, we can exactly determine where activation is because we're on the voxel level in terms of specificity, but of course the clusters that we find or the voxels that we find active are much, much smaller. Going back to our previous image, this is exactly what we see. So on the left, we have more voxels being active, so the clusters are larger. We have a more, well, areas that are in blue in this case. And on the right, the far right, we see that less voxels are active, but we know exactly where this activity is. And the trouble is there's no formal way of deciding these optimal thresholds. So as a researcher, you have to decide beforehand which threshold to use, and you have to stick with this. For example, if we pick a threshold of z is larger than 3.1, we have to, well, abide by these analyses, and we cannot just, because we've seen the data already, we cannot decide without compromising our family-wise error rate. Maybe I should use a threshold somewhat higher, or maybe I should use a threshold that's somewhat lower. There's no formal way to decide which is best. In the literature, often cluster extent and voxelwise thresholding are seen as two distinct or different things. Well, actually, cluster extent thresholding is sort of the larger part because we can sort of phrase voxelwise thresholding as cluster extent thresholding in a way. And this is because in cluster extent thresholding, we define the chance of finding at least one contiguous cluster of size at least k given threshold z under the null hypothesis of no activation to be smaller than a certain criterion. And in this case, there are two parameters that we can tweak, which is k, which we usually estimate from the data, and the threshold z, which we usually decide beforehand. So usually we decide z, so we decide on a threshold and we estimate the appropriate k value, for example using random field theory, permutations, or Monte Carlo simulations. But it's also possible to set k, which is the minimum cluster size, and estimating z, as long as sort of these random field or these permutations, the chances of finding a contiguous cluster under the null hypothesis still hold. So if you set k to 1, this results to a voxelwise threshold, meaning if you set k to 1, you have to estimate the appropriate z value that goes with it, and z will probably be pretty high. So we can also set a value of k larger than 1, and this basically refers to selecting a minimum cluster size one is interested in. And we can, for example, if we only want to look at clusters over, say, 1,000 voxels, we could tweak k and we, could decide the appropriate z threshold to use it with. And this is possible as long as sort of this, the upper statement of this slide holds. In addition to the issues with cluster extent thresholding based on the spatial specificity, there are more issues which are most of the time they pop up when we have larger number of participants. So not in your typical fMRI study where we have like maybe 30 to 60 to 100 participants, but in like these large cohort studies of thousands of participants. And this is an issue also that is more general with p-value based research. When the number of participants increases, the p-values get smaller, and in this case, in our functional MRI study, the clusters get larger for the same threshold. So for example, in blue you see activity for 33 subjects for this non-focal focal contrast at the threshold of z is 2.3, and the red-yellow activity is actually the activity for 66 subjects. So you see that the amount of clusters not necessarily changes, but the size of the clusters changes dramatically from 33 to 66 subjects. So for more and more subjects, usually what you would see is that the clusters under the same threshold would sort of be bigger and bigger and bigger, and then it becomes very hard to say anything about it because everything will be significant. To summarize this second part, voxelwise approaches are usually less powerful in detecting activation, but allow for proper localization of activity. Cluster extent approaches, on the other end, are usually more powerful in detecting activation, but are less spatially specific, and it gets worse the larger the cluster that you find. This is the spatial specificity paradox. There is no principled way to select this arbitrary cluster forming threshold. And with increasing numbers of subjects, the cluster extent becomes too large, with the same threshold, and this prohibits sort of a proper analysis of clusters. In this slide, cluster extent approaches are a suboptimal way to do inference because statements like this cannot be answered using this approach. For example, a statement like a large significant cluster contains a substantial number of active voxels is something we might intuitively expect, but we cannot say or answer using cluster extent thresholding. Statements like a large significant cluster is a more substantial scientific finding than a small significant cluster is also not true. In essence, it's the opposite. The smaller the cluster that we find, the more we are able to track its spatial location. And substantial overlap between a significant cluster and an anatomical brain area indicates evidence for the presence of activity in that anatomical brain area. So if we see these clusters and they overlap with a certain brain area, we usually want to make statements of these kind that we say, okay, it overlaps this area, so it might be indicative of using working memory, or etc., etc. And these are all statements that cluster extent approaches cannot answer.
Today's educational course is about solution to the problems of classical cluster extent inference. So we will talk about approaches based on recent advances in multiple testing, like true and false discovery proportions, closed testing, and joint error rate control. We'll talk about approaches based on effect size, so instead of p-values, and we'll talk about approaches based on Bayesian spatial modeling and on network-based data.
So what to expect of today? So we can actually quantify the number of truly active voxels within a or any cluster in the data without losing family-wise error control and thus increasing spatial specificity. We can leverage the information or the spatial correlations in the data to optimize this estimation. We can quantify spatial confidence bound for clusters, alleviating the increasing n problem, and we can use explicit statistical models to test spatial hypotheses.